Hello, in this video we'll be covering the rational zeros theorem, and it's to list the potential rational zeros of a polynomial function. Now recall, polynomial functions basically have two types of zeros. They're either going to be real or complex, but if they're real, they could either be rational or irrational. What this theorem does finds the potential rational zeros only. It will not find you the irrational zeros, nor will it find you your complex zeros itself. Okay? And remember, the rational zeros theorem will find the potential ones. So if it has rational zeros, for example, 2 is a rational number, 1/3 is a rational number, -4/5 is a rational number. So if a polynomial has a rational zero, then it will belong to the list that's given to you here. Okay? So now sometimes that list is quite lengthy. Sometimes there are 20 potential zeros. But if the polynomial has a real zero, or rational zero, it will belong to that list. Okay? So let's begin. So here's what the rational theorem is saying. Let f of x be a polynomial function of degree 1 or higher of the form f of x equals a sub n x to the n plus some other terms plus of a sub 0. When we first talked about polynomial function, I remember I discussed that these a sub n, the a sub n minus 1 are just real numbers, and that's all they are. And the leading coefficient cannot be 0, and the a sub 0 cannot be 0. Now, where each coefficient is an integer. Now, here's what the rational zeros theorem is basically saying. This is the bottom line here. If p over q in lowest terms is a rational zero of f, then p must be a factor of the a sub 0, the coefficient outside, or what we call the constant term, and q must be a factor of the a sub n, which is the leading term's coefficient. So it's basically all the possibilities of all the ratios of all the coefficients of the a sub 0 term and the a sub n term. Now, this is one of those situations that an example is very, very necessary to understand what the concept is basically saying. So let's see if we can look at one here. Okay, listing the potential rational zeros. So we're going to list the potential. We're not going to find them, but we're just going to see what the potential ones are going to be. And again, notice it says the potential rational zeros. It didn't say real zeros. Okay, there could be some irrational zeros as well that this theorem doesn't help us with. So, and it only will find the potential rational zeros. So we look at this, and this is a ratio of the factors of the constant, and the factors of the constant is going to be -12, and the factors of the leading coefficient is going to be 3. So it's going to be all the factors of -12 and all the factors of 3. So let's look at it. So all the factors of p, which is the -12, are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So to get the -12, I could be multiplying that first plus 1 times that last -12. Or I can multiply that -2 in the second one in the list times the positive 6 in the second to the last of it. So those are all the possible factors of -12. Now, q is going to be all the possible factors of the 3 out front. And it's going to be plus or minus 1 and plus or minus 3. So that list is considerably shorter, but sometimes it's long as well. So we're going to have to divide every one on top, the plus or minus 1, all the way out to plus or minus 12, by the plus or minus 1. And that's going to be part of the list. And then we're going to divide everything by the plus or minus 3 on the bottom. So as you can tell, the list is going to be quite lengthy. So p over q is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And that's what you get when you divide everything by the plus or minus 1. And now everything by the plus or minus 3, you're like, well, some of them are missing here. No, it's not. It's just already been listed. For example, the plus or minus 1 divided by the plus or minus 3 is the plus or minus 1/3. The plus or minus 2 divided by the plus or minus 3 is plus or minus 2/3. The plus or minus 3 divided by the plus or minus 3 is a plus or minus 1, which is already in the list. It's the very first one. And then the plus or minus 4 divided by the plus or minus 3, that's the last one on the list there. And then the plus or minus 6 divided by the plus or minus 3 is plus or minus 2, and that's the second in the list. It's already there. So plus or minus 12 divided by plus or minus 3 is plus or minus 4, and that's the fourth in the list. Okay? Now, this is not saying these are all the rational zeros of this f of x. As a matter of fact, we know that can't be, because how many zeros could there be altogether in the first place? It's 3, up to 3. Now, we don't even know if all of those 3 are even real. I mean, 2 of them could be complex, and 1 of them could be real. Alrighty? So you don't know what kind you're going to have. Now remember, Descartes' rule of signs still applies here. You can actually find the potential ones here. So, looking at just f of x, there's only going to be one sign change. The 2 in the middle does a sign change. So there's going to be one positive real zero there. Okay? Positive real zero. And if it's a 0, then it's going to be one of those lists if it's rational. So, so what you would do here is, if you want to see if any of those positive numbers are going to work, positive rational numbers are going to work, you could plug 1 in, plug 2 in to the function, plug 3 in, and use the factor theorem to see if it's 0 or not. And I believe one of them might be. Okay? So if you plug in 1, you plug in 2, plug in 3. Now they're not asking us to do it in this example. Okay? What they're saying here is just list the potential rational zeros. So if it has a rational 0, it's going to belong to that list. So let me just see what I'm saying. If I ask you if 5/6, that's a rational number. Is 5/6 a 0? You don't need to plug in 5/6 and see if it's 0 or not. It won't be. And the reason I know it's not going to be is because it doesn't belong to the list. P over Q's. So if a rational 0 is actually going to work, if it's going to be one of my zeros to this function, it will have to belong to that list. So, and again, the Descartes rule of signs, the maximum number of zeros a polynomial is going to have, and using the rational zero theorem, these are all tools that we're going to use eventually to figure out what the zeros of a function are going to be. And so now again, we don't know if this one has any rational zeros at all, as far as the negative ones are, but you would have to go through the list to figure out. So this can get quite lengthy, which means popping these numbers in here and testing them whether they're 0 or not can be very, very time consuming. But that's part of it. So at this point, the time constraints that you're used to having are out the window, okay? The times that it takes to do a problem to 2 or 3 minutes and then lose interest are gone. Sometimes it's going to take you 15 or 20 minutes to do one single problem. And that's just the way it is. And so you just have to be a little patient with these and just take your time and do them. Okay? So that concludes this example and this the rational zeros theorem. And I think in the next videos we're going to be actually finding the zeros themselves, and we're going to be using the last few videos to help us in that endeavor there. So you guys have a good day. You have any questions, as always, you feel free to contact me. Thank you.